Hi, welcome back to this video series on SMT solvers. Today I'm going to show you how we can synthesize a logic formula from given truth table. Okay, for example, you are given a truth table, made of 4 rows, right? And 2 columns, 2 known columns and 1 unknown column, right? P is a Boolean variable, Q is another Boolean variable, right? But you don't really know uh, the formula that goes to the third column. Okay, that's something we need to find out. It could be like you're trying to learn an algorithm, right? You're only sending inputs P and Q to the black box. So you can imagine like this: you have a box, you're sending inputs, right? You're sending P, Q. You don't really know what's happening inside the box. You're getting back some answer here. Okay, the question is, can we predict the logic, what's going on here? We don't really know what's going on here, but we wanted to sort of summarize the observation for all possible P's and Q's that we have observed in a compact way. So given a truth table, we would like to learn the high level formula. Maybe, it's nothing but P or not Q and something like that. Okay, so basically want to learn a formula given the truth table. Okay, the truth table can be like this, for example, TT, right? And it turned out to be T here, and it can be TF, could be something else here. We don't really know the logic that connects P and the Q. That's why I put a question mark here, right? So we wanted to learn what could be the transformation being applied to P and Q, Boolean connectors. Okay, let's say we are only allowed to use the Boolean connectors like OR and NOT. We would like the SMT solver to synthesize this for us. So I'm going to show you my example, how I model this, and let the synthesizer show us the output. Okay, so that's basically the plan. And what you're going to see now is the ability to automate this in a systematic way. So I was looking into a nice book, and I saw this problem. It's actually given to students to manually construct the formula that connects P and Q. There are 2 variables, right? As you can see, problem number 82 has question mark, right? The question mark that we need to find out. So what could be the valuable, what could be a formula that summarizes this? That's basically what I'm after, right? So I took this table, truth table as it is, and codified it here in SMT syntax, right? Basically, I'm going to use the syntax guided program synthesis technique to learn the model from truth table. Okay, that's what I'm going to do. So the truth table itself is codified here, right? When true and true was input, the output was true. That's basically what we saw on the problem statement. True, false, the output is true. False, true, output is false. False, false, the output is true. Okay, so what could be the magic F? We don't know the F. F is a black box. We wanted to learn. So we put some restriction on F. Okay, we say F can work with Boolean inputs, right? P and Q are Boolean inputs. So it's allowed to use OR and NOT. These are the allowed things, right? It's like a grammar. We specify the grammar. That's basically the idea of syntax guided program synthesis. And then we just let it come up with an answer for us. So let's see whether we can find out. Yeah, you can see it came up with this formula that the truth table is captured by this nice formula here. It says P or not Q. So let me write it for you. It says P or not Q. That's basically the idea of this synthesis, right? It was able to synthesize this formula for us. Let's see whether we can confirm this, right? This is basically the behavior of the third column, if you will, on the truth table. So let's go down and see the truth table and confirm that that's the case. Okay, so we can check it, right? When P is true, Q is true. Well, it doesn't matter what the Q is, because when we have an or, the first statement is true, so naturally get true. And this is also true, so we don't have to even worry about it. What about false? When P is false, look at not Q, okay? Q here is true, right? So not Q is false, therefore we get a false. So false or false is false. And P is false, so we go to not of Q, which is true. The Q is originally false, not Q becomes true, therefore R is true. So we got the formula based on this synthesizer. Okay, so as you can see here, the synthesizer actually came up with this function f for us, which takes two Boolean parameters P and Q as inputs and summarized this expression for us that matched the observation we expected. We can actually do more complicated things, not just two variables, okay? So what I did, actually, I prepared a table which is made of three Boolean variables instead of just two. And I'm going to show you how we can easily synthesize slightly more complicated formula, okay? So what I'm going to do is I plug in another variable, right? Because P, Q, R are my variables. And since there are 8 rows in the table, I actually typed it myself. I got off time to save time during the demo. So here is the table, right? P is true, Q is true, R is true. Then we expect the output to be true. So we need to come up with an F that satisfies all of these 8 rows, okay? So let's see whether we can synthesize one. Okay, well, yeah, that's basically it. Let's give it a try. Yep, it came up with a nice expression. So here is the expression, right? It says, let me just type it for you and we can compare. Let's see, we can, the inner part is, well, there is an outer part involving R. So we have P, R, right? And then an AND of Q and not R, right? So this is basically an AND of not R. Okay, so oops. Okay, so we can plug in some values and play with it and see whether that works. When P is true, obviously we get true for the last from 14 to line number 14 to line number 17. We don't have to do anything because P is true. Let's go to the place where P is false, because we are interested in the other cases. When P is false, of course, the first part has no use, right? Because it's false or something is the something part. What about Q and not R, okay? When we do not of R, this is the third column R, right? R is false. That means and will become false. So we got a false. That's consistent with our formula. When R is false, not of R is true. True and true is true. That's basically true we got, okay? And that's exactly what we expected the system to return. Okay, so you can check for yourself. The remaining ones work perfectly because you can see when Q is false, this part is completely false, and P is false means the whole thing is false. Okay, so basically this is how we can synthesize more complicated expressions from a given table. So from a learning perspective, right? If you wanted to sort of understand what a circuit is doing, you are sending some signal, true or false signal. Maybe there are 3 inputs or 4 inputs, whatnot, and you're trying to construct what's going on inside the circuit just based on the input-output, the observation. And then the program synthesis technique that I just talked about is called syntax-guided synthesis. I actually did this demo earlier on how to synthesize De Morgan's law. So if you're interested, take a look at those videos. And basically, that's all I wanted to share. Okay, thank you for watching.